Welcome everybody to today's webinar about build better battery cells faster. We have assembled a world-class team for you to inform you about the latest technology in battery cells development and research and production. Today's webinar, we're going to focus on battery slurry. We appreciate your time, appreciate that you spend an hour of your time with us. So we titled this webinar, Build Better Battery Cells Faster, because that's what we do. That's our job. I'm Christopher Schultz. I'm the Director of Marketing for Hioki USA, and I will be guiding you through this webinar today. Before we get started, I'd love to learn a little bit more about you. We have prepared a quick poll question that I hope you all participate in that. The first questions that I have is, what is your current role in the battery industry? Please select your choice. Are you in research, industrial research and development? Are you academic research? Are you in manufacturing? Are you in purchasing, which is super important these days? Are you business development, leadership, management, corporate management, or are you in a field that we haven't mentioned here? So if you can give us that information, we'd appreciate that. Let me give it a few more seconds. And I still see some answers coming in. Thank you very much. Okay, yeah, looks like most of you responded. Really appreciate that. Okay, so let's stop the poll question here and look at the results. Okay, we do have, most of you are research and industrial research and development, 96%, academic research, manufacturing, and business development are the next things. Thank you very much. Let's do the second question. Okay. Okay, can we get the second question? Okay, I think we do have some technical difficulties here.
Here, Chris, we already read it. It was together with the first and second one. Yeah, number two is right underneath.
Okay, thank you. Perfect. Thank you very much. All right, let's move on. We got, get this out of the way. A quick few words about, so now that we know a little bit about you, a quick word about Hioki. We were founded in 1935. That's a few years before HP, as a matter of fact. Our single focus is on test and measurement instruments that's related to power generation, distribution, power measurements, and battery testing. We have about 200 main product groups that solve real-world problems. You might know our zero flux current sensors or our milliohm resistance meters. A big focus at Hioki is on battery testing. We do have a market share of 63% in battery production testing, so some of you might know us very well already. And we continuously innovate and help you build better batteries faster. And that's what this webinar is about. All of our products are manufactured in Ueda, Japan. Our factories are zero emission certified since April 2021. Let me get a quick word about how we're going to run this webinar. We will have a moderated question and answer session at the end of the webinar. If you have any questions during the presentation, please type them in. You find a Q&A button at the bottom of your screen. We have a panel of experts that will answer your question in real time, and we summarize the questions at the end of the webinar. We will have a prize. We will give a prize at the end of this webinar, so stick around until the end, and you have a chance of winning a prize for yourself. The presentation will be recorded. It will be available tomorrow on our website. So if you want to go back and see what we talked about, you'll be able to find this on our website. Let me introduce our speakers real quick. First and foremost, we have a guest speaker, Jill Pestana. Jill works as the technical director at Electric Goddess. Electric Goddess is an energy storage and propulsion consulting firm. Previously, she worked as a senior scientist developing lithium-ion battery technology at Enovate, and is an inventor of 14 patents related to battery technology. Jill earned her master's degree in material science and engineering and her bachelor's degree in physics with a minor in music. Jill shares educational content on energy storage and electrochemistry on her YouTube channel, Across the Nanoverse. So go check it out, Across the Nanoverse. Very interesting channel there. She's passionate about innovating towards a sustainable future. Then we have Naomichi Miyagi. Nao-san is the product manager for the slurry analytical system and many other products at Hioki. He has been working for Hioki for more than 10 years and spent more than 7 years in the United States. In his early career, he was involved in building electric designs for our test instruments. Nao-san holds a master's degree and a bachelor's degree in chemical engineering from the Yokohama National University in Japan. Our panelists are going to be Ishan Daljic and Barry Bolling. Ishan and Barry, together they bring more than 25 years of experience in supporting customers like yourself in technology. If you ever called our call center, you probably talked to Ishan or Barry already. Ishan and Barry hold advanced engineering degrees from top-ranked US universities. Without further ado, I'd like to pass the word to Jill, who's gonna give us some exciting information.
Hello, everyone, and thanks for the fantastic introduction, Chris. It's a pleasure to be here. I'm going to take control of the computer now so I can start. I'm excited to share today about this slurry analyzer that Hioki has and just the science behind it and how it works and why we even do slurry analysis. So let's see. I should have control. Here we go. So to start, I think many of you are aware that the battery industry is growing exponentially. It's quite surreal to me to hear about these gigafactories coming up. It seems like a new one every other month. And just this graph, I think, sums up this growth that's predicted that just blows my mind. This was published by Statistica, and it just shows that growth between 2020 and 2030. There's over 5 times growth predicted from now to 2030 for batteries, global battery demand. And so we're really going to need to focus on making sure that we have not just the material resources, but also cell development and production to fill this demand. And I'm sure many of you, it sounds like, are researchers, so you're probably familiar with different types of battery chemistry. I love this chart. It really sums up this picture. It's from the Advanced Propulsion Center in the UK, and I found it in the Battery Report 2021 by Intercalation Station and the Volta Foundation, which are wonderful organizations and resources if you're looking for more on batteries. And this just shows you have the energy density on the Y plot and the cell cost on the X. And as you increase the energy density, you get more and more high performance cells. So at the lower end, you have LFP chemistries, sodium ion. And then as you move to the mid range, you have NCA, NMC, and CMA cells. And then for high performance, you have those specialty cells like silicon anodes, which I was developing at Enovate, also lithium metal anodes. and solid state electrolytes, which are all the buzz these days, right? And so while you increase the performance, you also increase the cost. And that's, I know, a major issue. As a researcher myself, I would love if I had an infinite budget to do all sorts of wonderful chemistry things and explore different materials. Unfortunately, once you're in the lab, that's not really the case. And so to accelerate innovation to meet this demand for batteries, we don't just need to improve battery technology, we also need to lower the cost of batteries, not just the material cost, but the production, the manufacturing, the research and development costs, and accelerate the time to production, right? So moving towards that red square there in that graph. So today I'm going to talk about how we can accelerate innovation using this slurry analyzer. To start, I'm going to make sure that I explain battery electrodes so we're all on the same page. So I'm sure many of you know what battery electrodes are. And then we'll go on to manufacturing battery electrodes. And I'd love to have your participation in these simulations that we're going to do. So I'll need your input, your expertise to help me. Then I'll go into what is electrode conductivity and slurry conductivity. I'll review R&D processes for battery electrodes, the current state of the art with that. And I'll finish with electrode slurry analysis, how it works. And I have this wonderful instrument, the slurry analyzer, LCR meter right here, which I'll be talking about. All set up for this talk. Exciting stuff. So let's get started. Battery electrodes. So battery electrodes are the components inside of the battery where redox reactions occur that enable a battery to store and release chemical energy. So the battery electrodes are where the magic happens inside of a battery. You see the battery diagram pictured there. You've probably seen this diagram many times if you work in the industry. The electrodes are the anode and the cathode. And if you've worked on supercapacitors or fuel cell electrodes, while those are also electrodes, they're a bit different than battery electrodes because battery electrodes store energy in 3 dimensions, not just 2 dimensions through absorption like a supercapacitor electrode. They involve intercalating the charge carrier ion or alloying with the charge carrier ion, which in lithium ion batteries is lithium, in sodium ion batteries is sodium, and so forth. Not only that, but they're not just the side of the storage, but also the energy conversion. And this is where they differ from fuel cells. Fuel cell electrodes don't store the energy itself, they only convert the energy. So you have these 2 very important functions that the electrodes carry out, and they're separated by a separator. I mean, it's a good name for it, right? Which makes sure that electrons don't pass through between the electrodes and short the cell. So the electrodes themselves, though, are conductive both ionically and electronically to complete those redox reactions. There are many different steps you can see here that go into making a battery electrode. And this is an important part of understanding how electrodes work and why they function the way they do and how to optimize their function. First, you want to mix together the slurry, which is a mixture of the electrode active material and solvent and additives. So active materials are what we typically call the materials that store charge carrier ions. This could be like graphite or silicon or whatever it may be. That, or I guess for a cathode, that's for the anode. For the cathode, it would be like LFP or NCA, NCM. Solvents are like NMP, and then you also have a binding material like PVDF, and you have additives as well, and often additives are conductive to improve the electrical conductivity of the slurry. The second step is the slurry coating step. You can see in that picture above on the right where you have a roller and the electrode has just been coated onto a foil current collector. It looks like a copper foil in this image. That's probably an anode. The third step is the drying process, and this is to evaporate out the liquid solvent from the electrode. Then you have electrode calendaring, which is kind of like when you take dough and roll it with a rolling pin to flatten it out, increase it or decrease its thickness, increase the density. It's typically a pressure and heat process. And while it's just these few processes, maybe some more or some less, like maybe you don't calendar your electrode. Different R&D manufacturing processes choose different processes in them, but each process can be fine-tuned in order to optimize the performance of the electrode itself. And I've listed in those tables all these different parameters that could be involved in modifying that electrode to reach its optimal performance. So it seems like a simple process, but it's kind of complex. And here, I just want to give you some images up close of a battery electrode. I think these are important to look at to see what is a battery electrode. As an R&D scientist, I performed probably over 200 hours of SEM alone on battery electrodes and other materials. And so I'm really familiar with these kinds of images. And you can see on the left is a picture of a graphite anode up close. You can see those particles. They're about maybe 10 microns diameter, most of them. And on the right side, you have the NCM cathode, a nickel, cobalt, manganese cathode. And on the bottom, you have cathode particles themselves, which I think look a lot like blackberries with the secondary particles and primary particles. So those are just, I want to give you some visuals of what we're talking about when we're talking about battery electrodes. Battery electrodes have so many properties that all correlate with cell performance. And here are just the key ones that I think are important to show. So you have not just the formula, how much percent of each material, you also have the composition. What are the materials going into these? The particle types, the size distribution of particles, the morphology of the particles. You also have the bulk properties of the electrode, like the tensile strength, the compressive strength, the strain, and the ductility, because battery electrodes experience a lot of stress inside of a cell as it completes redox reactions. Then you have the microstructure, which that picture on the left is a cross-section of a battery electrode up close using scanning electron microscopy. And there you can see a cross-section of those cathode particles. So these are only, it looks like 15 microns in diameter about. And you see the carbon binder domain, the CBD, and the pores inside of this. It's a very complex composite with a lot of different dimension to it. And so understanding that microstructure can influence, or that microstructure itself can actually influence the performance of that electrode inside of a battery. You also have, of course, the energy density and the conductivity, both the electrical and the ionic. So here we are. I hope you guys have been listening and want to participate. I'd really appreciate your participation. I think you all are excellent researchers and engineers, and so I'd like to hire you as quality control engineers. And my question to you is, we want to ramp up our manufacturing line of a module, a battery module. And here are the various steps that we currently have, but I'm wondering, in your professional opinion, which of these parts of the battery do you want to inspect first in order to optimize that quality of the battery module and catch production and process issues early? So select whether it be the slurry, the electrodes, the cell stack, the cell, or the module. And I'll give you a couple minutes for this. We want to make sure that our battery has that optimized performance at the end, catch any issues early, like batch to batch variation. Maybe someone made a little error in the manufacturing process, a machine drips some oil where it's not supposed to, who knows what, right? The whole, when we're thinking about process engineering and quality control, it's really about making sure that you're saving time and improving the efficiency all the time. So thanks for answering. I think we have 19 of 23. That's pretty good. So we can end this poll. And most of you, looks like you selected the slurry, followed by the electrodes, and then the cell stack. So most of you want to inspect the slurry first. And I would have to agree with you on that. Where's my next slide? There we go. I would have to agree with you all who has selected slurry, because I think when we were first making a slurry, if we mess up the slurry and we don't find out until we make an electrode, until we go through all those steps, which take time and energy and labor and resources, then we could have, spent more than we wanted to on this issue. So of course, there's no right answer for this, but that's what I would choose. And I think that's what the majority of you would choose. So it's a great exercise to think about, you know, why it's important to inspect materials. So here again is the table of electrode properties. Now, the holy grail, like the dream of any researcher in batteries, is to understand how individual properties of these components and materials and processes affect the overall cell performance, affect how a battery capacity fades, how the battery degrades. So how can we understand and measure how each property affects cell performance? And how can we design that slurry to optimize the cell performance in the end? These are billion-dollar questions here, right? So let's dive into electroconductivity, the focus of this talk. And this particular, we can look at a lot of different properties, but here we have the slurry analyzer that measures conductivity, right? So electrode conductivity is the rate at which electrons can move through the electrode to the current collector. You need that electrode to complete the circuit in a battery after it completes a redox reaction. And why is electroconductivity so important to battery performance? I can think of a couple reasons that I'll share here now. The first, especially in the EV industry that I see, and in just aircraft batteries too, where you need high power, fast charge batteries. In a battery, the redox reaction or the rate of charge and discharge are only as fast as the slowest process inside of the cell. And so that means if we increase the conductivity of the materials, including the electrode, we can increase the rate at which it can complete those redox reactions to charge and discharge. And it won't damage the cell as much, because we could go really fast for charge, but we may damage the materials, which leads to the second point. The long-term performance of a cell is definitely affected by the electrode conductivity. Batteries start degrading and dying from the moment they start cycling, unfortunately. And it's all about gently letting them die, right? We're going to be cycling them. We can't control the entropy inside of the cell as reactions take place, but we try to control it as best as possible. And by controlling, I mean, we want to keep the impedance of the cell as low as possible for as long as possible during the cycle life of a battery. And low impedance or high conductivity maintains the battery's capacity and performance. Electroconductivity plays a role in maintaining the optimum energy capacity, minimizing capacity loss over time. I know when I did work with silicon anodes, silicon, as you may know, expands a lot upon lithiation. And so in order to make sure that as it expands, it still remains electrically conductive to the electrode and to the current collector, so that you don't get isolation of the silicon where it no longer dedicates its capacity towards redox reactions. You need to have enough electric conductivity things in the electrode so that it can be electrically conductive, even as the silicon particles may expand or break apart. And so issues also like irreversible chemical reactions and thickening of the solid electrolyte interface, or SEI, can be improved by increasing the electrode conductivity in some cases. There are cells, like I'm pretty sure LTO cells actually don't have an SEI on the LTO, but other cells like graphite-based, silicon-based, even for a cathode like a nickel-based cathode, LFP-based cathode, those form what's called a CEI, and increasing their conductivity can help mitigate the issues with the insulative CEI or SEI thickening over time. Currently, when we are analyzing the electric properties of the electrode, we use on the right, you can see the electrode resistance meter, which Hioki sells one. It's pretty powerful and awesome. And they also have battery testers, right? So you can test the electrode electrically, you could test the cell itself electrically, but there's not really many tools available for the electrical properties of slurry until now. But historically, one of the major tools that's used is a rheometer to measure its viscoelasticity. And so by adding this ability to measure the electrical properties of the slurry, you can do a lot of work to fine tune that slurry formulation to maximize its electrical conductivity before you spend the time and energy and resources to make the electrodes. And so not just like developing a better electrode, but you have more parameters, more measurements that you can use to understand slurry mixing processes and methods and improve those processes. And you can also start to perhaps correlate that cell performance itself to the slurry properties for a greater understanding of materials and chemistry. That can really accelerate R&D as you get those answers. And on the manufacturing side, like we did earlier, we realized, hey, you can catch issues early if you start analyzing from the slurry level, and you can use that slurry analyzer to measure the quality and consistency of slurry production. So how does the slurry electrical properties work? Like, what even makes a slurry electrically conductive? Because it's a liquid, right? It's kind of like this grainy, slushy liquid, a slurry. So in the first process to make the electrode is to mix the slurry together, mix all the components. And if you think about it, it's like when you make a cake, which I have a YouTube video where I talk about how a battery is kind of like making a cake, if you want to check that out. But I'm going to use this comparison, this metaphor again. If you're making a cake and you have, say, the batter or the eggs and the milk and the flour, and you're mixing them together, at first, when you're first starting out mixing it, there's not going to be a high dispersion. You're going to get clumps of the flour and clumps of the egg and clumps of the other materials. And so because they're in these isolated clumps throughout the batter, you're not going to have any kind of conductive networks in the slurry in order to conduct through the whole thing. And so your conductivity is going to start low, your dispersion is going to start low. But as you increase your mixing time, like if you're mixing cake batter, mixing muffin batter, whatever you want, you're eventually going to get a higher level of dispersion. And that's when you get that conductivity network happening in the slurry after it's been mixed a bit. But if you mix it too much, you can disperse the materials too much, and those conductive networks may go away. And so you may think, okay, I just know how to optimize a slurry. I just mix it for a really long time. It turns out that may actually decrease the conductivity of that electrode over time. So finding that right moment is so crucial. Finding that balance between material dispersion and formation of conductive networks is key. And here's a graph to display that. And those agglomerates that start with low amounts of mixing, that can actually result in a roughly surfaced electrode that could puncture the separator, causing a short circuit. So we're not just talking about making sure it's conductive, but also safe to use inside of a battery. And those conductive networks are essential for the electrons to move and complete the redox reactions. So you all did such a wonderful job as a quality control engineer that I'm promoting you to an R&D scientist. So my question to you, we're going to be producing NCM 622 cylindrical cells. And I want to know how to improve the anode and cathode conductivity while decreasing the amount of material that we need to use, because we don't want to have to make batches and batches of materials to test this process. So my question is, here's the process in light blue from slurry formulation to formation. And in red is the equipment selection that we have for our R&D process. You can see our formulation is in the bottom corner, the graphite, carbon, black, NMP, and PVDF for the anode, and the NCM622 for the cathode. And my question is, which of these options for analysis should not be included? Because we only have room for 4 of them, unfortunately, in our budget. If it was a perfect world, we'd have all 5. But which one would you say we shouldn't really do if we're doing an analysis? So remember, this is a cylindrical cell. That's important to note. And we want to improve the conductivity of the anode and the cathode. And so which of these would you not want to include in your R&D process? And honestly, I don't know if there's, a right or wrong reason for this. I'm curious to know if you disagree with my opinion, why that is. So maybe you can answer in the questions. If you think, no, I think it should be this way. Like, I'm really open to hearing your opinion I think this is a interesting question. Oftentimes this happens in R&D, right? You don't have the budget for everything you want, so you have to pick and choose what you think may be best for what you're trying to achieve. So maybe we can wait a few more minutes. We have 10 more people to go. Okay, good. 13. Awesome. So distribution looks like most people are saying, oh, skip the cell cycling analysis. We don't need to see the performance of the cell. Skip the strain test. We don't care how bendable the electrode is. Skip the 4-point probe. We have the slurry analyzer. That's enough. And skip the slurry rheology. Oh, the slurry analyzer is the least now. Slurry rheology, because we don't need to know about the viscoelasticity of the slurry. Great. All right, I think we can stop there. Thank you so much for participating. So this is great. We have such a different distribution, right? So it seems like we're tied to eliminate the cell cycling and electrode strain test from our measurements. So this will be interesting. Okay, I want to hear if people disagree with me. So I'm gonna close that, head to the answer. So what I would say is to skip the slurry rheology in this case. And the reason for that is, first of all, the slurry analyzer will help understand the conductivity, which is what we're investigating. And then as we move down the line, the 4-point probe will validate, in my opinion, it'll validate that slurry analyzer result. So we'll understand, how does the mixing, coating, drying, or the coating, drying, all of that come into play. And actually, I kind of messed up this graph. I'm sorry, y'all. The slurry analyzer point should be between mixing and coating. So my mistake. And then the strain test I would actually include, because this is a cylindrical cell. And so the electrodes have to be wound tight in a roll for that. And if they're not, if we don't test for the strain, it could crumble. And so as we develop the electrode, we need to make sure it's flexible. So I would actually leave that in. And then the cell cycling analysis, I think it's just really important for any R&D process to have, because we need to know, we could make an electrode, make a cell, but we need to know how it's going to perform in the end. So I did say, maybe we don't need the slurry rheology, because as long as we have the conductivity, it's good enough. I don't know, maybe you have different opinions, love to hear it, but thanks for participating. So this slurry analysis, the slurry analyzer behind me, wait, let me give you a close look. So here's the slurry analyzer, and then you fix this special test fixture over here. It clips in seamlessly, and excuse me. And so this instrument measures 3 different parameters: the DC resistance, the R ratio, and the uniformity. And I'll get into what these measurements are specifically, but first I want to share, how do you even measure conductivity of a liquid slurry? It's pretty complex. And if you think about it, slurries makes up the active material, the conductive particles, and then insulative materials like the binder and the solvent. And so this slurry, actually, the best way to measure it would be an AC impedance spectroscopy system. There's these relaxation processes that occur within the material and the contact with other material. And so understanding the relaxation processes is important to quantify that conductivity. So in that middle picture, you can see the electron conductivity occurs not just within the bulk of the single particles, but between particles as the electrons exchange down the chain of conductive additives or particles. And each electron exchange between particles can be modeled as an RC equivalent circuit. So you have there a resistor and capacitor in parallel. And if you have experience with EIS, that's wonderful. EIS is called electrochemical impedance spectroscopy. It's also termed AC impedance spectroscopy. Either way, I think you can phrase it. And I have videos on my YouTube channel about this process. So if you're interested in learning more, I encourage you to check those out. But in this presentation, I'll just cover what's here. So here on the left, we have a plot of the AC impedance measurement. And we also have on the y-axis, we have negative X, which is the imaginary impedance. And on the x-axis, we have R sub S, which is the real impedance. And there we have an analysis, the data we get from the slurry analyzer showing the conductivity, the properties of that slurry. And this can be fitted to an electrical equivalent circuit, very similar to a common way of analyzing battery EIS data. And there you have resistors and a constant phase element in parallel. And so because those particles between them, there's a double layer, it acts as a capacitor. And then you have the resistance for the electron transfer as well. So that models each of those different electron transfers. So after you fit this electrical equivalent circuit, or EEC, to your slurry data, you can do this analysis. And actually, Hioki's software does it for you, which is wonderful. It saves you a lot of time and effort. And you get these three different results. The first is the DCR, the DC resistance. And this is calculated by taking that equivalent circuit and adding up the sum of all the resistive values. So you get the total resistance in ohms. And then you have the data for the R ratio, the resistance ratio. And R lambda is the average resistance of all those different equivalent circuit units divided by the total resistance. And then you also get the uniformity. So the uniformity is the conductive material relaxation distribution. And what does that mean? So if you think about a capacitor, this relates to the capacitance of the system. If you think about the impedance of a capacitor, the equation is Z, or the impedance, equals 1 divided by the square root of -1, or J, times omega, the frequency, times capacitance. So you may want to write that down. I should have put this equation in this presentation, but I didn't. So Z equals 1 divided by I omega C. Now, that's for an ideal capacitor. For this system, the capacitor isn't ideal. And this CPE index, or P sub lambda, relates to this exponential factor that ranges between 1 and 0. And so it's 1 for an ideal capacitor, 0 for, I mean, it never reaches 0, but as it approaches 0, you get unideal, I guess, capacitance. And so by measuring this uniformity, you're getting how close is my system to an ideal capacitor? How close are these equivalent circuits to an ideal capacitor? And lastly, I have 2 case studies to share about this slurry analysis, because you're probably wondering, this sounds great, but have you actually demonstrated the technology? And yes, Hioki has demonstrated this technology. So the first study is looking at the difference in kneading times or mixing times of the slurry. So you have the same content ratio, solid content ratio. You mix it for 0, 1, 2, or 6 minutes, and then you add an NMP, the solvent, until the solid content concentration reaches 50%. And here's the results for, on the left, you have that total resistance value, which you can see is low at the beginning for 1 and 2 minutes. You have low resistance of the slurry, and then it increases after 3 minutes. And then for the R ratio, you see that percentage starts out pretty high and it decreases a little bit as you mix it. And then the uniformity, you can see it increases. So that solution is becoming closer to an ideal capacitor type of situation. The second demonstration is changing the solid content ratio, specifically of the conductive aid or conductive additive. And of course, as you increase that conductive additive in that graph on the left, you decrease the total resistance. I mean, that's intuitively what I would think would happen. Also, you increase that R ratio as you add in more conductive additive. But this uniformity, check out this is different. So it first starts pretty low and then it increases for that middle point and then decreases for the last point. So as you add more conductive additive, you get this more ideal like capacitor situation, followed by, oop, I went too far, it decreases. So then they went a step further and went, okay, so we got the electrical data for slurry. How does this reflect on electrode sheet? And as you can see that the electrode sheet resistance actually mimics the slurry resistance, to show that, you can actually analyze your electrode sheet before you even make it, which saves a lot of time and effort. So that's incredible. So awesome. So thank you so much for listening and participating. Today we covered the slurry analysis for manufacturing. We can see that it can detect production issues and help with quality control from the first stage of cell production. And it can also help us understand our cell properties and performance better and process improvements better for R&D. So now I think we have a wonderful demo of the slurry. Gonna hit play. So here we have the slurry being filled into the sample holders. And the test fixtures on the cell, you insert that sample into the instrument and start the measurement. Save the file, always an important step, and start the measurement. You can see it displays it in real time what those values are. And then it has built-in software to help you do the analysis through the system. You can select the active material, you can select the additives you're using and submit and analyze those. So it has these presets for all of these materials. And you get your results. And you can compare data. Always a nice feature to have. And here it seems like they're grouping them based on different properties so that you can look at how different similar properties or similar samples behave. And then you can always download your results. It comes out in a CSV file, which you can use with Excel. And I think that's the end of the video. Yep. Oh, we're starting over. Let's watch it again. Just kidding. Okay, Chris, you want to?
Yeah, we can watch it again. No problem. It's fun to watch. It's even more fun to actually play with it.
Yeah, I'm really excited to use mine.
Hey, Jill, thank you so much. That was very enlightening. I really appreciate the explanations. Let's see. We have a few questions, answers, a few questions that we're trying to answer here. So if you still have any questions, please type them in the Q&A window. There's a button at the bottom of your screen. Click that button and type the question in there. We're going to answer them now. We have a few questions during the presentation. Let's get started. So first question, can we use the slurry analyzer for solid state batteries? Who wants that now? San, Jill, I think you both are the right person to answer that question. Solid state batteries, can we use the slurry analyzer for solid state batteries?
I guess I'll start. I'll say, yes, this definitely seems applicable to solid state batteries. I think it'd be very interesting to study the slurry of solid state batteries, especially if they include an analyte or a catholyte material in the slurry formulation itself. And those are because it's ionically conductive. And so perhaps when you're analyzing the electrical properties of that, both electrically and ionically conductive slurry composition, you can maybe see features of the conductive ions in the EIS or AC impedance spectra that you get. So it could be a really interesting experiment to explore with that. I don't have experience with it, so it could be really interesting. Maybe somebody here has.
Yes, so I agree with you. And so slurry analysis is start from impedance measurement. Based on those data, we're gonna analyze impedance and also using predefined equivalent circuits of the slurry. We can identify our ratio, uniformity, and DCR. So if I believe solid state battery use similar materials that is used in the conventional one. So we can choose the similar. We can choose write equivalent circuits, and then we can analyze the impedance data.
Cool. We need to try that out sometime. So let us know if we should try this out with your solid state battery technology. Very interested in seeing how it works. Let me go to the next question. Here's a question: does the time affect the rheology? And I think the question is related. The time is related to the needing time.
Yeah, so we have done slurry analysis, and electrically and mechanically, internally, and yeah. So when we mix materials too much, viscosity can be improved, but uniformity, no, our ratio value decrease. So we need to find a kind of a sweet spot of mixing time and other parameters.
Yeah, and I think the next question relates to that too. That what is the optimum? What are the optimum parameters to achieve good slurry with improved conductivity? Is there any general answer for that? Are there any trends that you can
I'm trying
identify?
to think. I mean, it really depends on what your starting materials are for that slurry and how those materials interact with each other. So it's hard to say how to achieve a good slurry. I guess common ways to improve the conductivity are adding a conductive additive, but adding too much could also be an issue. So also just the active material particles, understanding whether those lend any conductive benefits. I've worked with conductive materials that have a lot of impurities in them, and I think it definitely improves the conductivity, especially silicon that is doped is more conductive, right? Because it's a doped semiconductor. And so things like that can change your conductivity. But, there's so many parameters with mixing, the type of mixer you use, the temperature, the atmosphere. So it's hard to say for what the actual way to optimize it is. You just have to experiment.
Similar question, related question. Do you find a correlation between slurry viscosity and conductivity? I guess the question is, can you just measure viscosity and then know what the conductivity is in general?
Yeah, I think for this, it might seem intuitive that if the slurry is less viscous, it may be more conductive. Like you may think just because it's really runny, it's more conductive, or you may think because it's thicker, it's less or it's more viscous, it's more conductive. But I really am a strong believer, batteries continually surprise us. If you're in battery research, that they tend to do unexpected things and cause you to have more questions than answers. And so again, I would say for each system, it may be different, and it's important to explore that using these kinds of tools.
Then I've got a very practical question. How long does it take to run a sample on the slurry analyzer?
Takes 1 minute, right?
Yes, 1 minute for impedance measurement, and another minute is needed for impedance analysis. So 2 minutes, I think.
2 minutes total. So almost real time.
Oh, that's so
almost
quick.
Yeah. So here's a very interesting question. I think there's two questions really that relate to the material groups. There's one question: what happens if the material that specific company is using, or the specific research group is using, is not part on the slurry analysis software? And I think related question: how about lithium sulfur batteries?
Okay, so we are trying to increase the number of materials we analyze with the software. So, but at this point, still, the number of materials is limited. So you can analyze impedance data based on existing list, but we can also add new materials in the list. So that this requires making new models for analysis, and we are going to ask you to take some impedance measurements for new materials. So this exercise this exercise allows us to add new materials. So you can choose those materials afterwards.
So in other words, Naosan, if it's not there, talk to us. We'll help you get it in and get your measurements done. That's part of what we do. That's how we work with the slurry analyzer. Perfect. So I've got one more question. Do you recommend handling the instrument in a vented hood?
I mean, I would say, of course, it depends on your slurry and how toxic that is. If you're working with a chemical like NMP, I would verge on the side of putting in a hood if you have the space in your lab. I mean, it is a fairly compact system, but I do think if you're limited on size and if your slurry is, you're not so worried about any kind of volatile compounds, there is a lid on the sample holders themselves, which may be able to just, you can seal it in a ventilated space like a fume hood or glove box, and then carry that to the instrument. Though I don't think it's airtight, of course, if you need it to be like have no contact with the atmosphere. So what does your team say on that? Is that
Naosan, anything to add to what Jill was saying?
No. Well, so we need just we need a slurry, small amount of slurry, which is just 1 milliliter. So yeah, so if you can put this small amount into the vial, we can analyze it.
Yeah, in general, health is important, right? Don't risk your health over over an experiment. Yeah, usually your site safety officer would have guidelines, recommendations, what you can do and what you should not be doing. But yeah, toxic chemicals, you always want to be careful with that, obviously. Okay, I think we've got most of the questions covered. Please ping us if you have any other questions. We are here for you. We're here to answer any questions you may have. Let me move on before we hit the hour to the next part of the seminar, and that are the prize winners. We put all your names in a virtual hat and pulled 3 winners out. The prize is going to be a 1-month license of the slurry analysis software. And the winners are Mary R, Daniel K, and Gabriel M. Mary, Daniel, Gabriel, we will ping you with the email that you registered with. Let us know if that's possibly wrong email or if you want to have another email. So if you contact us too, that would be useful, but you expect an email from us within the next day. And so you can collect your license for the slurry analytical system from us. Congratulations. We're looking forward to your feedback and to your experience with the slurry analytical system. So with that, I want to thank you all for attending, for spending an hour with us. I want to thank Jill for the awesome presentation, and for Naosan and the panel for the answers that you've been provided. I hope that webinar was useful. If you have any questions, please contact us. We are located in Dallas, Texas. Plano is a suburb of Dallas. Phone number is right here. Email is over there. Follow us on YouTube, Instagram, LinkedIn. We are very active there with updated videos and updated posts. And please check out Jill's YouTube channel at Across the Nanoverse. Thank you very much, everybody. Congratulations to the winner. Let us know if there are any questions. And with that, I'm signing off. Thank you very much.
Thank you. Bye.